Hey, Honors Physics, this is Mr. Hausman, and this is the third video in a series for students who may have been absent or catching up or just want to relearn some of the key ideas involving electric fields. So if you're watching this video, then you've already been introduced to what an electric field is. It's a vector quantity that describes the area around a charge. That field is responsible for what we believe is the electric force, but only when you put a test charge or a small charge in that electric field. So this unit or this little section is about quantifying that force. Okay, so quick review. So fundamentally, we all have lived our entire life in a gravitational field. It's toward the center of our planet. And the force that is created by it is called your weight, right? We call it weight casually, but it's really the force of this gravitational field. So what creates it? Well, it's a force experienced by anything with mass that is placed in a gravitational field. So you take a rock and you hold it up in the air and then you let it go. And it's going to start falling. It's because it has a force acting on it. Now, how do you know how much force is acting on it? Well, the formula right here at the top that we've used since about October of this school year. So what's G? Well, G is actually the gravitational field. It can also be considered an acceleration, but really what it is a number that describes the amount of force that is created per 1 kilogram of mass. So if you hold a 1 kilogram mass up in the air, let it go, it will experience a 9.8 Newton force downward the entire time. And of course, we have to multiply that by whatever the mass is. It doesn't have to be 1 kilogram. It can be a 5 kilogram cinder block. It can be a 1,000 kilogram car, right? They all have weight. They all get pulled back to Earth. On the other hand, an electric field, believe it or not, has many similarities. And I hope you notice that when you look at these two formulas, you notice that they are set up exactly the same. So you have a ton of experience with Fg equals mg. So now all we have to do is know that there's a new force being created. It's the force experienced by a charge that's placed in an E field. And so how do you figure out how big the force is? Well, instead of mass, you replace that with a charge, and you multiply it by the strength of the E field. And that E field is not a fixed number, but it could be something like 90 newtons per coulomb if it was very weak, or it could be 10,000 newtons per coulomb. In fact, in the lightning video, they went up to 25,000, if not more, when we were looking at the storm clouds out in New Mexico. Q is, of course, how big is the charge, and that's measured in coulombs. So the electric field is a vector field or a force field. It's a field that's going to create a force. So it has a magnitude and a direction. It has a vector to it. And we've already learned how to draw the lines. The lines show the direction of force that a positive test charge would feel. If someone says, which direction does it go? It goes the same direction as a positive charge. Now, how do you draw those lines? They come out of positives and they go into negatives. So let's review kind of how that would work visually. So gravitational fields accelerate masses. Here's a mass, and maybe it has a velocity sideways, but as soon as there's a gravitational field acting on it, which way does it accelerate? We know that the acceleration is downward. In fact, we used to always write it as negative 9.8 meters per second squared. That's the G field. Electric fields, on the other hand, what do they accelerate? They accelerate charges. We're summarizing. And they can be at rest. They can be moving. You don't know this yet, but that's a hint at something we're going to learn later. So it can be any charge, whether it's at rest or it's moving. So here's a charge now. So here's where it gets a little different. Here's a major difference between gravity and electric fields. So masses only accelerate one direction. They go in the direction of the G field. But here, a negative particle would go against the E field and curve away from E. A positive charge would curve with the E field. And so That's a major difference. E-fields are more flexible depending on what you put in them. They can push or pull. So let's look at this. So here's an E-field, and there's a positive charge in it. And what we know is that its force is going to be the same direction. Notice this, we have two different vectors, and they're going the same way. An electron, on the other hand, or anything negative, would go the opposite. Okay, same direction versus opposite direction. Positives go with, electrons go against. Next page. So here's some practice problems to see if you really get it. And they're sort of like puzzles. They're not really hard puzzles, but let's take a look. So first off, here's the principle you're using. Forces on charges are the same as the E field for a positive, and they are the opposite of the E field for negatives. So these are word problems, but let's visualize it. An electric field points to the right. A positive charge moves also to the right. Now, moving to the right means it has a velocity. It's just moving. And so what's going to happen to it? Well, we know that positives go with E fields. In fact, you can kind of hide this velocity. You don't even need this. All you need to do is say a positive in an E field, it goes the same direction as the E field, and the correct answer is therefore to the right. Consider pausing this video right now and trying all of them on this page. When you're ready, unpause the video, and I will have all of the answers there for you. You're going to notice that for all of these answers, we actually didn't use the direction of the velocity. All we had to do was read if there's an electric field down and there's a negative charge, then the force must be against that electric field. Let's go to the next puzzle. The next puzzle has to do with the fact that forces create accelerations. In fact, it was Newton's second law that describes that right here. Forces and accelerations not only make each other, but the direction of the force, and you already know how to do that, is always the same direction as the acceleration. That was a subtle detail in Newton's second law when we used to calculate net forces, and then you would calculate an acceleration, and you did that a lot right through the midterm exam. That's something that we often maybe overlooked, that the acceleration is the same way, but it's really good to reinforce that. Now, the next two bullets that guide this page, I know I just bracketed 3, is that velocity and accelerations are both vectors. So remember we said we were skipping the velocity? Now we need to pay attention. So if you can figure out the direction of the force and the acceleration by reading, is it a positive, is it a negative, which direction is the E field, the next thing you have to do is say, well, is it going to speed up or slow down? So if the velocity and the acceleration are in the same direction, they speed up. We use that a lot this fall when we were doing kinematics. If they're in the opposite direction, they slow down. Now, there's one more possibility. What if the velocity and the acceleration are perpendicular to each other? Well, then the charge will turn. Now, all three of these are accelerations, slowing down, speeding up, and turning, and you have to figure out whether it does one of those three. So let's do one together. An electric field points to the right. A positive charge, let me just change color. A positive charge is also moving to the right. So it sounds like the very first problem on the previous page, and it is. But now I don't want to know the direction of force. I want to know what happens to its motion. How does its motion change? And none of the options are to stay constant. It either slows down, speeds up, or turns. Well, here's the process. Positives get pushed to the right, so their force and their acceleration are to the right. And now you look at the direction of the velocity and you look at the direction of the acceleration, they're both to the right. They're going to speed up. Hit pause now and try the next ones on this page. Hit unpause and check your answers. There you go. Check your answers, have conversations with other classmates, or check in with me if you're not getting the next, this page correct. Puzzles. Second to last page, I stand corrected. This page is the same, but each of these problems, let's get a color out here. Each of these problems, and there's actually 4 per line, 1, 2, 3, 4, each one has a different unknown. On the first four, you have to figure out what charge, positive or negative, would experience that pair of fields and forces. In the second one, what's the direction of the force and the acceleration? Notice there's no forces, so you would draw in a force. For example, a positive charge in an E field would experience a force toward the bottom of the page, downward. And then the last one is draw in an E field. Which direction? So do you notice that there are 4 problems per row? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hit pause and try this page. Did you get all 12 right? The charges are in the top row, the forces are in the middle row, and the fields are in the last row. Okay, here's how we finished this puzzle day. We took a look at what I call escape rooms or mazes. So if you've never done an escape room, what you do is you walk in one door. In this case, you're walking in by yourself and you figure out what to do in that room. Maybe there's clues, maybe there's hints. In this case, all you have to do is ask the question, which way, right? Which way would I get pushed? By the E field. And then what you do is you trace the path. You say, would I go forward? Would I go up? Would I go down? Would I go left? Would I go right? So a positive charge that enters into an E field to the right would keep going straight. Now you're in the next room. Some very complicated escape rooms have multiple rooms, and you have to go from room to room until you get out. Now you go to a new room, and the E field is pointing downward, and you know that that's going to cause you to turn. And so what you've just found is that the exit is letter D. So you can think to yourself, which direction is the force? And then show me the trajectory, show me the path. So here's another one, but now it's negative. It goes into an E field, but it goes opposite an E field. Negatives go opposite an E field, so they turn right. And then this one exits through D as well. Now, you're like, what about the last box? Skip it. It was just there to fill up the 2x2 grid, but you don't always go through every single room. Okay, you finish the last two and then check your answers. So there we have it. You've mastered the skills needed to describe the direction of force, acceleration, and whether the object speeds up, slows down, or turns. Now, when I say object, we're talking about all charges. Charges turn, speed up, or slow down in E fields. Hope that helped.